What about the Diophantine equation study? David Hilbert's 10th problem titled Of the Possibility of Solving a Diophantine Equation raised the question in 1900 of the existence of a general algorithmic method with a finite number of steps enabling to decide, for any Diophantine equation, whether this equation has integer solutions or not. This may seem a very low requirement, as one will then not know how many solutions exist, nor will it give their precise values. However, even for so small requirement, Yuri Matyasevic's theorem answered to Hilbert's question in 1970 by the negative. It establishes that Diophantine sets, which are the sets of integer solutions of a Diophantine equation with parameters, are exactly all recursively enumerable sets, which means that such an algorithm cannot exist. So what? Should we be discouraged for even a yes or no question cannot be answered? Will we always have to restart an exercise when going from one equation to another? Do only specifically adapted methods or use of brute force have any chance of being useful in this mathematical domain? What about to beat the odds? What about adding an ingredient, that is, to add asymptotic approximation, in order to address a wide range of equations? What about to recover then some ambition? Our focus will be to determine a general method to get an asymptotic formula for Diophantine equations with an infinite number of solutions. The same method can be used to identify the solutions in a given Diophantine equation with finite number of solutions. However, special care of results interpretation is then required. We will only provide a sketch of the method, but links to more information are given at the end of the presentation. So let us start. A Diophantine equation is a polynomial equation with one or more unknowns and integer coefficients. Let us take an example. John Friedlander and Henryk Iwaniec showed in 1997 the infinity of primes, y, being written as x1 square plus x2 at a power of 4, where x1 and x2 are integers. An asymptotic formula was then also provided. The present method will systematically give a result not only for one value of c, which is 0 in the Friedlander-Iwaniec example, but for any integer value of c. In fact, we are unable to get the asymptotic formula without considering all values. Doing that, it happens that the y-dependent part of the formula remains unchanged. This is not further developed in the hereby sketch, as the most interesting part is the evaluation of the fudge factor r depending of c as shown here. To get this fudge factor r of c, let us go back to the equation and operate a trivial rearrangement. We would proceed in the same way with any other Diophantine equation, that is, the c parameter is on the left side of the equation and we isolate, on the right side, each independent variable expression. Separation is systematically a plus operation. Minus is within the parenthesis and multiplication of two variables can only be handled as an aggregate of independent variables. Instead of looking for the solutions in x and y unknowns, we attribute integers values on x, prime values on y, and seek results for c. Therefore, obviously, we will never get results just for one c value but to the whole range c-dependent equation as we told before. This c parameter is central to our method. We call it the target. It requires all of our attention, and so effectively it really does. Don't you agree? The next step is then to find the adequate operation enabling to get the fudge factor r. This is the matrix multiplication. In a symbolic way we write this as shown on the board. Let us describe now how to get the value of each matrix and how to attribute the result for each value c. In order to achieve that, we have to return to fundamentals. It consists in the following mathematical implication which leads to a modular equality. When all the parameter pi, i2, i3, ipi, tend towards infinity, the implication will no more be just an implication but truly an equivalence. We have to tackle with infinity, which may not seem an easy thing, but wait to see. Let us first observe that we can decompose the unique modular equation in this way. Now, this may even seem worse, but again please wait to see. Let us look at the last line of the set of equations. Let us suppose that, for some IPI value, we get the same result with IPI plus 1, then the same will apply to IPI plus 2 and so on up to any higher power. We call IPI the degree of stability corresponding to the prime number pi. When this occurs systematically, for any prime, a lot of the previous infinities disappear altogether. When this does not happen, incorrect values of the fudge factor do appear, leading to only approximate results. But approximate values may sometimes be sufficient as long as we do know the fact. Note also that the smaller pi value, the higher its effect on the fudge factor are. Therefore, special care has to be addressed to the case pi equals 2, which is sometimes not at all a trivial affair. Let us now focus on the way to go from the general modulo equation to the set of individual modular equations. Our concern is not in the solution's values, but how many we get for a given C value. We note the result #C. What we do, is to run goToNext loops for each variable, where we attribute values from 0 to pi to the power IPI minus 1. IPI is here the degree of stability. Therefore, replacing IPI with a higher integer value would only multiply the number of occurrences #C by a pi factor, which provides no additional information for #C that we wouldn't be able to get in another trivial way. We have here three nested loops. The viewer must realize that if IPI is large, the resulting calculation may be very tedious or even impossible. But when variables are independent, fortunately, this can be done by addressing each loop separately. The viewer will observe that the first loop here, which corresponds to a variable taking only prime numbers values, is treated in a different way than the two next loops dealing with standard variables taking integers values. As shown, the loop contains an additional condition skipping all the instances where the variable is a multiple of pi. This condition is necessary and sufficient, and the origin of this specific treatment is explained in our mathematical articles. Having then the three loops results on #C, we are able to process back with the adequate tools to get the aggregate result for the initial equation. We will not go into explaining all details here, but for variable y, the steps of the matrix construction is shown on the board. 1. Start with the matrix for a standard integers variable noted x of degree 1. This requires to consider the case of C equals 0 and C different from 0, giving a matrix of rank 2. Note that all matrices are square. Since in the initial equation, we have a degree 4 variable, we need to expand this matrix to an adequate size, which is to a 1 plus 4 rank. When this is done, all we have to do is to subtract the unit matrix to get the intermediate needed matrix, this process being a universal recipe. For higher degrees, the matrices are more complex, of course. In particular, the matrix components will depend on the pi modulo values as shown for x1 to the power 2 in the case of pi equal to 1 modulo 8. This may seem tedious, but once you get the resulting matrix, it can be reused in any kind of polynomial equations containing the x to the power 2 monomial. As we explained, once all the individual cases collected, one has only to proceed with matrix multiplication. Here we get these results. The g parameter is one of the primitive root of the prime number p. The hashtag values are those of the corresponding #C values. The fudge factor requires an additional constant value multiplication called normalization in order that the fudge factor will not diverge when all p values are taken in account. This then gives the final expression. Numerical research show the asymptotic evolution waves, but nevertheless smaller and smaller deviations from the exact values of #C. The method enables to process more complex examples. Let us suppose we wish to enumerate prime numbers z of the form x to the power of 3 plus x to the power of 2 multiply by y plus x multiply by y to the power of 2 plus y to the power of 3 plus 5 multiply by t to the power of 2 plus 9 multiply by u to the power of 4 plus 4. The basic bricks to handle the problem are then, processing of the multiplication by a constant, here 5 and 9, processing of monomials like u to the power of 4, processing of the x to the power of 3, plus x to the power of 2, multiply by y, plus x, multiply by y to the power of 2, plus y to the power of 3, aggregate of variables, and then to finish with, overall processing. The final constant, here 4, will be replaced by the target integer c. The choice of variables, either being integers or prime numbers, is also free, pending on a mere unit matrix difference. The viewer will find more on the subject at either of the following links. He will find the Friedlander Iwaniec example, but also the main article, which give the comprehensive in-depth record. There is also a lot to say about the Hasse principle, which is at the heart of the problem, and when the viewer is done with all of that, there is an article on the finite number of solutions case. We wish you a pleasant reading. What about some comments underneath after that?